So good afternoon. Here we are with another remote seminar. Our guest today is Charalambos Pittordis from Queen Mary, University of London. Charalambos had a very interesting career path. So he got the PhD in 2018, working in probes of cosmology and gravitation under the supervision of Will Sutherland, who's still a collaborator of himself. Now he's working actually as a data scientist in the second largest investment and management firm in Europe, handling 2% of global assets, but he's still participating and working in the astronomy community. And today he's giving us a talk about testing modified gravity with binaries with GAIA Data. So please, the stage is yours.
Thank you very much, Franco. So, testing out my Italian. Buongiorno a tutti, mi chiamo Charalambos Pittordis, and I'll be speaking to you all about testing modified gravity theories using wide stellar binary systems from GAIA. So, throughout this talk, I'm going to give a brief introduction to GR versus modified gravity theories, and then discuss a little bit about wide binary systems themselves and as probes of gravity, and then discuss about the GAIA spacecraft. Then I'll move on to discuss a little bit about how we actually perform tests of gravity by constructing some simulations and computing observables. And then the last part of the talk itself, it will be using results from GAIA itself. So us going out and searching for these wide binary systems, and then ending with a summary and conclusion. So, as we know, to date, the best description we have of gravity on all scales is general relativity. It has been very well tested to high accuracy on solar system scales, and even Lambda CDM model that's based on GR with the inclusion of dark matter and dark energy fits to cosmological observations very well. And it can also explain the weak field limit. So things like flat rotation curves of galaxies, the CMB, and so on, with the inclusion of dark matter. However, there is a problem. The problem is that we do not have a direct detection of dark matter. So because of this, some theorists may speculate that maybe GR is not the correct theory for gravity. Maybe it needs to be modified. So then theorists will go ahead and modify gravity to try and explain the dark sector effects of cosmology. So by modifying dynamics, putting in extra fields and all this stuff. Now, no modified gravity theory has been successful in actually fitting to cosmological observations. But there is still a large model space for modified gravity theories, which still remains partially explored. So moving on to our probes of gravity, which are the wide binary systems. So what are these systems? So these are isolated stellar binary systems with very large separations, where the gravitational interaction between these two stars is comparable to what you see in the Milky Way galaxy, acting on systems that are greater than 8 kiloparsecs away. So regions of the galaxy where you start to get the flat rotation curve effect due to dark matter or maybe a modified gravity theory. 80% of the stars within the Milky Way galaxy are stellar binary systems. So even a fraction of that 80% of them being wide binary systems is sufficient amount of data for great statistics. These systems, they should not contain any significant amount of dark matter. So meaning that their orbit should just be purely Newtonian / Keplerian. And yes, these systems may be tidally disrupted by other external sources and stuff like that. But if they are tidally disrupted and they unbind, they will unbind on scales much less than the age of the galaxy. Hence, there should be a clear distinction between currently bound binaries and tidally disrupted binary systems. So, using them as probe as gravity. So why do we need another probe of gravity? Why use wide binaries? I mean, we have great gravitational experiments, so stuff that we've done on the solar system scale where we have constrained the parameterized post-Newtonian parameters. We have this amazing binary black hole mergers giving us gravitational waves, and also the recent one with supermassive black hole imaging. So what do wide binaries actually offer? So what wide binaries offer, they actually help us constrain the Newtonian part of the gravitational field, i.e. the time-time part of the weak field metric in GR at the very low acceleration regimes. And this is complementary to all other tests of gravity on all scales. And also, these are purely model-independent probes of gravity, which I'll show you guys later on. Now, these systems, they have received little attention in the past because of their very long orbital periods. And also their relative velocities are extremely slow. And in the pre-Gaia era, there wasn't any instruments that was precise enough to measure such slow relative velocities. However, in the pre-Gaia catalogs, they were selected quite fairly robustly using their proper motions. But again, because of their very slow relative velocities, it wasn't precise enough for any useful dynamics. And also in the pre-Gaia era, there's also a magnitude range where there's missing wide binary systems. And in this magnitude range, there's a potential of thousands of wide binaries actually existing, bright enough for any follow-up radial velocity measurements from ground-based telescopes. Now, moving on to discussing a little bit about Gaia. So Gaia is coming in to save the day. So Gaia is this spacecraft that's measuring proper motion, parallaxes, and properties of over 1 billion stars within the Milky Way galaxy and producing this 3D map of our own Milky Way galaxy. And with this unprecedented precision, we can get very good, precise proper motion measurements and parallaxes for our wide binary systems. However, the distance precision on Gaia isn't good enough to be able to resolve the line of sight separation. So knowing the distance between star being in forward or behind each other in the sky. And also the radial velocity instrument on Gaia isn't that great. But however, ground-based telescopes are. So by having Gaia giving us the proper motions, the projected velocities, projected separations, luminosities, and having ground-based telescopes giving us the radial velocity measurements, this should give us 5 out of the 6 phase space parameters, which should be enough to actually perform our tests of gravity. So now, moving on to how we actually perform tests of gravity using these systems. So we begin by constructing simulations. So we simulated around 5 million different unique type of orbits for each theory of gravity. So giving them different shapes, sizes, orientations, and so on. So in the case for modified gravity theories, however, these orbits are not really defined by just a simple 7 major axis and eccentricity. These orbits are defined with an effective orbit size and a quasi-eccentricity. And what we see is that these definitions actually coincide with the usual 7 major axis and eccentricity that you will use in a standard Newtonian gravity, which is great because it means that we can keep all of our initial conditions consistent across all gravity theories. So if we see which type of theories we're actually testing, we are testing theories that are dark matter emulators. So things like MOND with different interpolating functions, Tevez, emergent gravity, and the external field effect. And the external field effect theory is a property of MOND. And the way this theory works, it's the idea of the external field from the Milky Way galaxy, let's say, is also being applied or acting on the internal gravitational field within a stellar system that resides within the Milky Way galaxy. And what this is happening here, it's violating the weak equivalence principle in GR, i.e. getting rid of the idea of freefall. So if I show you guys an example of what these modified gravity theories look like within wide binary orbits, you get something that looks like this. So by using the initial conditions of the eccentricity being 0.7 and the 7 major axis being around 15,000 AU, you get to see that, as we expect in the Newtonian theory, we get a closed orbit. In other modified gravity theories, we see that the orbits tend to precess quite a bit. If you look at the external field effect theories, as you can see, if you increase the value of the external field effect from 0 to 1.5 A0, you see that the orbits start to become more and more Newtonian-like. So the orbits are great and all, but as we've said before, we cannot observe a full orbit solution because a full orbit solution takes 100 to millions of years, and we cannot live for that long. So, but what we can do is we can observe a snapshot of the phase space parameters. So, i.e., taking each point of an orbit and computing the observables. So, and what we do is we study the joint distribution of the projected separation of the wide binaries themselves, and also looking at the 2D velocity ratio. And this ratio is the ratio between the relative velocity of the orbit itself and the circular Newtonian velocity for that current projected separation. And this velocity ratio is a very convenient parameter to use, because when you look at the 80th and 90th percentile values of this distribution, it becomes nearly independent on an unknown eccentricity distribution for wide binary systems. To explain the last point in a little bit more detail, so if we take the case that we have all of our parameters very well measured, so i.e. we have the full 3D velocity ratio, and we look at the probability distribution comparing three different types of eccentricity distribution, which is in this plot here, we see that when we get to larger and larger velocity ratio values, we see that the 80th and 90th percentile values comparing the three eccentricity distributions starts to become indifferent, which is good because it shows that it becomes nearly independent. In reality, we only have 5 out of the 6 phase space parameters, so we have to make do with the 2D velocity ratio, because the component that we are missing is the line of sight separation for wide binary systems. But there isn't that much of a difference. I mean, the only difference is that the 2D velocity ratio is basically the 3D velocity ratio just shifted to smaller values. So now if we actually look at the observables of the sample orbit movie that I have shown, and we look at the joint distribution, we see that we get something that looks like this. So this root 2 limit that you see going horizontally is the root 2 limit for bound orbits described in Newtonian theory. So in Newtonian theory, nothing should ever go beyond or above this point, whereas in modified gravity theories, they tend to go beyond this point, giving us a nice clear distinction to do some comparisons. So this is just for one orbit. If we do this for 5 million different types of orbits, we get a scatter distribution that looks like this. So here we are comparing the Newtonian description against modified gravity theories without an external field effect. And as you can see, you have a very nice clear distinction with the majority of the orbits being above this root 2 limit. If we are comparing theories that have an external field effect and have different values of the external field effect, you see that they start to become quite similar to the Newtonian description, where you'll have some that will just leak over this root 2 limit. If we look at these plots in projected separation slices and we look at the histograms, we see that in this example here, comparing against theories without an external field effect, you see that when we get to larger projected separation values, these modified gravity theories start to shift beyond this, well, now vertical square root 2 limit relative to the Newtonian theory. So this should be very robustly or very easy to detect or rule out some of these theories. When we look at theories with the external field effect, we see that their orbit and their distribution starts to become quite similar to the Newtonian description. But however, for us to actually do some good tests and measure any shifts from the Newtonian theory, we require a very large sample of wide binaries, and we need to study the 80th and 90th percentile values. And if we look at the 80th and 90th percentile values in a little bit more detail, we see that, yes, the shifts are quite small, but they still remain non-negligible. So with a good sample, we should be able to measure around 4 to 8% shifts relative to a Newtonian theory. So if we start to consider some observations and what type of samples we actually expect to get, so as we have said, theories with an external field effect, we need a large sample for useful statistics. So if we start putting down certain conditions in certain mass ranges using a certain luminosity function and binary separation distribution with our desired range and so on up to 200 parsecs, we actually estimate that we can achieve around 10,000 wide binary systems, which is actually a great amount of data for great statistics, because even with just a sample of 1,000 well-measured wide binary systems, we can actually detect an offset or a difference of around 4 to 8% relative to a Newtonian prediction. And yes, and this is the case of if we can actually control all systematic errors, contamination, and things like that. However, there are some observational caveats. And the main observational caveats are things like contamination from unbound pairs. So there might be two stars that are in the sky that may appear to be a wide binary system, but they're just uncorrelated or unrelated stars that masquerade as a binary system. And also one of the other main problems is that some binary systems might be a hierarchical system. So one of the members of the binary system itself might be its own binary system, which will affect the velocity measurements. But however, doing follow-up radial velocity measurements and getting precise metallicities and things like that, we should be able to calibrate out these effects. So now moving on to the last part of the talk, now we've actually went to GAIA and we got ourselves some data. So we went to search for some wide binaries and we aim to try and produce a very clean, unperturbed sample of wide binary systems. So we put in conditions like magnitude less than 16. So trying to get sources that should be bright enough for follow-up radial velocity measurements, up to around 200 parsecs and so on. And in addition, with our sample, when we were searching for wide binaries, we cut out things like the galactic plane, clusters, and we try to remove as many hierarchical systems as possible, and so on. To show this visually, we started off with close to 1 million stars found in the GAIA. And then after searching for our wide binaries and doing some cleaning, we ended up with around 24,000 potential wide binary systems. So as you can see here, we've cut out some clusters, we've cut out the galactic plane, and so on, to make sure that our wide binary systems are isolated systems and they're not affected by any other external sources. So with our data, we found, well, we computed the projected separations, and the projected velocities and so on. And by having the magnitudes, we can use the mass magnitude relationship and we can compute the circular Newtonian velocity for that current projected separation. So one of the parameters used within our 2D velocity ratio. So by having all of these together, we can then go ahead and actually do our scatter plots. And what we get is we get something that looks like this. So, so the red distribution, the red scatter plot, is the actual observed data of wide binary systems. The green is modified gravity theories without an external field effect. The magenta distribution is a more realistic external field effect model. And as we've shown before, the black is always the Newtonian description with the √2 limit for bound orbits. So I'm not claiming anything here that, oh, there is modified gravity theory or new physics or anything like that, because in this plot, it's only the projected velocity over the circular Newtonian velocity. It's not the full 2D velocity ratio that we need to use, because we are still missing the radial velocity measurements that we need to get from ground-based telescopes. But however, if we look at the projected separation slices of that distribution, we see that for modified gravity theories without an external field effect, so the pure dark matter emulated theories, we see that when we get to larger and larger projected separation slices, it starts to not correlate and shift away from the actual observed data. So I guess we can kind of safely say these theories are pretty much ruled out. But however, if you look closely in these plots here, we can see there's actually a tail distribution in each one going beyond this √2 limit for bound orbits. So then we start to think, okay, what can this tail distribution actually be? So we thought, okay, maybe it might be some chance projected stars. So maybe stars that appear to be wide binary systems and so on. So we did a couple. So we did a couple. Yeah, thank you. So we did a couple of simulations, and we saw that when we do simulations for these random chance projections, we saw that the tail in the actual observed data is much more numerous, more populous than the randoms. So we see that, okay, this is clearly not due to any random chance projected stars. So then we thought, okay, maybe there might be flyby stars. So conatal flyby stars that come from the same open cluster, which has dissolved. And these stars appear to fly by together outwards. And we thought, okay, we take that simulation and add it to the Newtonian distribution and try to fit this to the actual observed data. And once we fitted this observed model to the actual data itself, we saw that there was actually a pretty good fit with acceptable chi-squared values, which you can see in points here. However, there is some inconsistency, and the inconsistency is that the fitted number of flyby systems decreases when you start to increase the projected separation slices, whereas in the simulations you actually meant to get more flyby systems at larger projected separation slices. So at this moment, this tail still remains as a mystery, and we're still trying to figure out what's actually going on and trying to get a better understanding of flyby systems and stuff like that. So just to summarize, wide binaries give a great opportunity to perform tests of gravity because they reach very low acceleration regimes and they contain no significant amount of dark matter, and it's a pure model independent test of gravity because you only need the velocities and the projected separation and not much else. And it's also complementary to all other tests of gravity on all scales. And what we see is that it's very easy to detect and rule out some theories without an external field effect. So a lot of the dark matter emulated theories. And but theories with an external field effect, we need a large, good sample of wide binary systems to study the 80th and 90th percentile values. And to conclude, so we actually have a very good large sample of wide binary systems. And our desired range that we're actually really focusing on is projected separations of around 3 to 20,000 AU, because if you go to separations much larger, there are more observational caveats and other challenges at these larger separations. And also modified gravity theory effects actually start to appear at values greater than 5,000 AU. So in the future, what we're trying to do now, we're trying to improve the purity of our wide binary sample, and also trying to produce more simulations to correct for more systematic errors, contamination, or try to model a hierarchical velocity distribution to see how that fits in with stuff, and so on. And recently we have actually submitted an observing proposal for a pilot observation of around 50 wide binary systems, so around 100 stars themselves. And once we get this subsample and we have our radial velocity measurements, then we can start to see if there's something else going on in the tail, if there's more flybys, hierarchical systems, and so on. So this should give us a lot more information to understand what's going on. And in the future, hopefully this subsample expands to a larger sample. And if it expands to a larger sample, then we should be able to have great statistics, well, better statistics to perform pure model independent tests of gravity at the very low acceleration regime. Thank you all for listening, and I hope you're all staying safe at home, and I'll be happy to answer any questions that you all may have. Thank you.
Thank you. Impressive, impressive work. Okay, so I am far from being an expert here. So I would happily leave the stage if anybody from the audience want to raise any question. Or otherwise, I can start. Okay, Stefano Ettore is asking. No, sorry. The message was, Stefano, can you speak?
Yes. Hi, thanks. Very nice talk. I'm just wondering if you have some radial velocity already in hand that can be used to test at least preliminary your results. I mean, because I expect that this system were already followed up by spectroscopy.
So in terms of radial velocity measurement, if the, so I mean, if you know any good instruments that are available now to do some radial velocity measurements, then yeah, that would be great. But yeah, so our sources that we're actually looking at, they have a magnitude range between sort of 12 and 13. So we're keeping it below 13 for our pilot study because they are bright enough for the proposal that we put in, which is for the HARPS telescope using the EGGS mode, just to get a pilot study and get a feel of our radial velocity measurements. And the sort of radial velocity measurements that we're actually looking for is something that can precisely measure radial velocities of around 0.05 kilometers per second. So things are really extremely slow. So I hope that has answered your question.
Yes, thanks.
Just to better understand, when you say that in some of the model you tested, there is also the inclusion of the external field model.
Yes.
How does it exactly work if you are testing such a big distribution? I mean, I think I understand the external field in this case would be the external field from the galaxy itself or from a larger scale environment. Am I correct?
Yeah, so it's the idea of the external gravitational field of the Milky Way galaxy is also acting, or is adding on to the internal gravitational field between two stars within a stellar system that's within the Milky Way galaxy itself. And the idea is that if you've got this external field effect acting on systems within an internal system within the Milky Way galaxy itself, or in our case, binary systems have an internal gravitational field between the two stars, and then you have the additional external gravitational field from the galaxy that's adding on to that. What would the orbits actually look like? And what we see is that we actually get something that's very similar to Newtonian. However, this theory is also a little bit dependent too on, it has an angular dependency and a radial dependency from the galactic center.
So when you are applying this to the observed sample, you need to guess the distance of every different star, I guess, to impose the potential at that location. At least the radial.
Yes.
Okay.
Yes. So we try to determine the orientation, the phase space, how it's projected in the sky, every way possible in actually getting velocity measurements for these systems.
Okay, thanks. That answer. Then we have other pair of questions. So if Valentina Cesare can speak, I would just let her ask the question. Otherwise, I can read. Okay.
So I have two small questions. Thank you. So the first one is in the scatter plot, the 2D velocity ratio is plotted against the distance of the wide binaries from us in astronomical units.
Are you looking at this scatter plot or the simulated? Oh, this one.
This one.
So this one, it's so we don't have the full 2D velocity ratio because at the moment here we have the velocities from proper motions from Gaia itself only divided by the circular Newtonian velocity for that current projected separation. So we still don't have the full 3D relative velocity to scale it with this circular Newtonian velocity for this current projected separation. So this is why we need to do the follow-up radial velocity measurements so we can get the full 3D velocities and see what these orbits actually look like, or maybe this scatter above here, they might be hierarchical systems or something else going on. But once we actually do the radial velocity follow-up measurements and we find out, okay, this is all contaminant, then we can clean this away from our sample.
Okay, so yes, it was because on the x-axis I couldn't see the label, so it's the projected.
Oh, you can't see the label on the x-axis.
Yeah,
oh,
we have a banner of.
Yeah, that's projected
it's
separation.
The projected separation. Okay,
yeah, I think. Oh, there you go.
And so another small question, and so according to all these tests, so the best theories of modified gravity that you've tested are the ones that include the external field effects, right?
Yes, at the moment, the ones with the external field effect are the ones that are, well, it's not as good as the Newtonian theory at this point here, but it is putting up a good fight in actually doing some fits here to the observed data. So theories without the external field effect, so things like MOND and its interpolating functions, emergent gravity, and theories like that, we can safely say they'll rule out. And I guess we can say they are fully ruled out once we have this follow-up radial velocity measurement.
Okay.
So I'm not trying to make anything concrete or claim anything at this moment because there's still more information that needs to be collected.
Okay, thank you very much.
You're welcome.
Okay. Any more questions from the audience? Anywhere from Italy? I don't see any. There is a quick one I read here. Have you tried some of the Gaia rotation velocity? Radial velocity, sorry. Radial velocity. I guess it's radial velocity.
So we did try, however, it's I just tried it for fun to see what type of things that we get. But however, for the radial velocity measurements from Gaia, the instrument is not great. It's not that accurate at all. Hence why we need to do follow-up radial velocity measurements. So we need something with an accuracy that can reach 0.05 kilometers per second. But we can use the radial velocity from Gaia. It wouldn't be accurate, and there will be very large errors.
Okay.
Sorry, it's just curious. So I noticed that actually all of your targets are actually bright stars, and for those bright stars, Gaia radial velocity can reach 0.1 something. So how different would this introduce to your results if the accuracy of the radial velocity, like from your requirement 0.05, if it is 0.1, how large it will be, the uncertainty, if you use this not good enough data?
So with the uncertainty, so if I try and remember my notes so I think we need pretty good uncertainties.
Yeah. What if the uncertainty is 0.1? If
it's 0.1 kilometers per second in Gaia, well, 0.1 kilometers per second error, I think from what I remember, we needed something that was much less than that, because I think around 0.1 kilometers per second, it still becomes quite difficult to get the absolute velocity from GAIA itself, and also it becomes quite difficult to determine or distinguish whether if there's some contamination or anything like that. So
okay, so 0.05 is the requirement to distinguish different models. Is that 1 sigma or it's
so I can't remember, I apologize, but if I do remember, I'll send you an email and give you details.
thanks.
But yeah, so I'm trying to remember at what. No, okay. So yeah, I apologize. I can't remember, but I'll send you an email later on in terms of accuracy and what type of errors that we are actually looking for. So we're trying to be very, very precise with these measurements to make sure that there is nothing else going on.
Okay, thank you.
Okay, or you can send the detail later to me and I can forward in case.
Yeah, not a problem.
Okay.
Thank you very much.
Okay, I think this is it. Thanks a lot. I'm going to stop the recording now.